So what are the three primary results of the chapter? Well, they are, first of all, and this is up on the board, you can take a look at it, though you recall this very well, I'm sure. The result about central angles, it's not really a result, it's like a definition. It's what we mean by arc measure. The measure of an arc is the same as the central angle that cuts that arc. Okay, that was the first sort of foundation of the chapter. Really, it is sort of the primary foundation because everything comes out of that when you take it together with results from previous chapters. And then the first of the important results that was proven in this chapter is the inscribed angle theorem, which again, there it is on the board. Uh, though you can look in your notes or you can look on the theorem sheet, and it's the very simple result that an inscribed angle, that is an angle whose sides are chords, is half the measure of the arc that it cuts. Now, what we'll talk about today is this, the third of the three foundations of the chapter, and it's about tangents. And I do think that I talked about this with you when I first introduced the myriad, or near the time that I first introduced the myriad, because there are many myriad problems where this is the result that you use. And there are actually a pair of results here, okay, about tangents. So let's talk first of all what we mean by the word tangent, and then we will prove some results about tangents. Now, first of all, something I meant to look up, but I forgot to do so, and I will do this and talk to you next time about it. Okay, so this word tangent, you have seen it before, I know. You saw it back in the chapter on trigonometry, and then you would think to yourself, well, this obviously has something to do with the tangents from trigonometry. And it does. And I have a vague recollection of what that connection is, though I'd have to go and verify that, so I won't talk about it today. This, however, is a distinct sense of the word tangent. Okay, so don't think that just, oh, this is a right triangle and this is a ratio of side lengths. That's not what this means. Okay, it means something else. It means something related to that, but it does mean something else. So, what is the something else that it means? Well, I will tell you the something else that it means. A tangent is a line related to a circle in a particular way. The first part of the relation is that they are coplanar, which you probably would have presupposed, but I should say it anyway. So they're coplanar, a line in a circle, and moreover, that line and that circle intersect precisely once. Okay, they intersect precisely once. That's what the term means here. Now, there's something I should emphasize right away. What I should emphasize is this, is that the mere definition of what I mean by the word tangent does not by itself imply that tangents to circles exist. You can state a perfectly meaningful definition, and yet nothing actually exists that satisfies that definition. So this is something that we talked about before, but I have another example for you. I came up with this a few years ago. Sometimes it's fun to rediscover what I did at previous years. Here's a word for you. The word is squozen. Here's the definition of squozen. A squozen is a positive integer whose square is 12. Think about that for a moment. A positive integer whose square is 12. First of all, you understand precisely what that means, okay? You would be able to correctly pick out a squozen, if any existed. However, do squozens exist? 3 squared is 9, 4 squared is 16, so no, there cannot be a squozen. But that's a perfectly well-formed, that's a perfectly meaningful definition. It just so happens that it's impossible that there be any squozens. Now, the point is the same about tangents as well. I have proposed for you a definition of tangent. It does not follow from the definition alone that tangents exist. Now, you probably find it plausible that they do. Do you think it's possible for a line to graze a circle, to intersect it at precisely one point, not penetrate into the interior, and so presumably intersect it twice, but just intersect it once? Does it seem plausible? Yes, it seems plausible, but you know that plausibility in this class is not enough. So let us actually establish that tangents do actually exist. And the way that you establish existence in this class is this. And this goes all the way back to Euclid. If you look at Euclid's elements, his theorems are of two basic types. One where he proves a property of some object that is already given, like, I don't know, you're given an isosceles triangle and you prove that the base angles are equal to one another. Another is to prove that a certain kind of object exists. So it's not that you have an object already present and you prove that it has a certain property. Instead, you prove that a certain kind of object exists. And we've had a number of proofs like that. You remember when we proved, for instance, that if you've got a line and a point not on the line, then there exists through that point a line parallel to the given line. We proved this, okay, that it does exist. And how does that go? How does one prove existence in geometry? Well, one carries out a series of allowed constructions. And then when one is done with the constructions, one pauses to think about what one has constructed. And one proves, as a matter of fact, that it satisfies some description, okay? And that's what we did with the existence of a parallel to a line through a given point. I said, hey, carry out this set of constructions, which involve lines and angles and so on. And then, let's reflect upon what has been produced. It turned out that it had to be parallel to the given line through the given point. We're about to do that as well with tangents. That is, I'm about to carry you through a certain set of constructions, all old familiar constructions. When they're done, we'll pause and reflect upon what has been produced, and we will prove that in this production, what we have made, there is a tangent line. Okay, so here we go. How does this go? So we start with a circle. Okay, so think of this as a multi-stage process. So start with the circle. You see here circle A. Point B is a point on the circle. Construct then radius AB. Okay, so again, think of this as a multi-stage process. The circle is center A, and then B a point on the circle, and then the radius AB. And then let us construct line M through B perpendicular to A. And these are all allowed constructions. We can construct a radius because we have the center and we have a point on the circle. And then we know that we can construct a perpendicular to a given segment. That's in the list of allowed constructions. Now, my contention is that this line M that was produced, that was constructed as a perpendicular, it's a tangent, okay? That perpendicular to the radius through the point, through the radius's point of intersection with the circle, that must be a tangent. And what that means is that we have to prove that this line M intersects the circle precisely once, okay? We already know by construction that it does intersect the circle at least once, because we constructed it so that it would pass through B, and B is a point on the circle. So we know, just by the way the construction was done, that the line does intersect the circle at least once. Now we need to prove that it doesn't also intersect the circle again. That's the real task here. Yeah.
Okay, we're you do it as what's it called, the antithetical proof.
Indirect.
Indirect proof. Yeah. Construct the theoretical.
No, I really like the name antithetical proof because it's kind of antithetical.
Construct a point along the hypothetical point.
Yeah.
It would intersect again. Then create the radius going from A to that.
Right. You saw it in a flash. He had a geometrical epiphany.
With two right angles, which can't exist.
Damn. You saw the whole thing. Oops. I recorded myself saying damn. Ooh, I just did it again. I should probably stop saying damn. Ooh, sorry, third time. Yes, but that is correct. Do you see what just happened? He saw exactly the form of this proof. Did you feel it? Did you feel that it was about to be indirect? I mean, obviously, Cole, you did. Perhaps some of the others of you did. So we wanted to prove that that perpendicular couldn't intersect the circle a second time. So assume that it does. Hey, look, it does. The second point of intersection is at the C. And remember what we did in the construction. We constructed M so that it would be perpendicular to AB. And then look at this. So C is the second point of intersection on the circle. So AC is also another radius. So like Cole said, we now have an isosceles triangle CAB. One of its base angles is a right angle, which then implies that the other base angle must be a right angle as well. And so now we have a triangle with two right angles, which is, of course, impossible. But that means that this line M, which was perpendicular to AB, cannot intersect the circle the second time. But it did intersect the circle once, so it intersects once and only once, and that means that indeed it is a tangent. So the real upshot is this, is that you want to make a tangent, here's how you do it. Make a perpendicular to a radius through the point on the circle, okay? That's how you do it. Now, there's also a converse of this, okay? And here's what the converse says, and the converse is true as well, and they're both important results. The converse says this, it says that if you have a line that is tangent to a circle, okay, so this result says, make the perpendicular, this will be a tangent. So short form, if perpendicular, then tangent, okay? The converse will be, if you have a tangent, and then you draw a radius out to that point of tangency, that is that unique point where the tangent intersects the circle, then that radius will be perpendicular to the tangent, okay? So if tangent, then radius drawn to point of tangency perpendicular to tangent. So that's the next result that we have to prove. So here's the setup. We've got the line M, that is, let us say, tangent to the circle. So that's the given. B is the point of tangency. That is the point where the tangent intersects the circle. And then we construct an AB, the radius to the point of tangency. And what we will prove is that AB is perpendicular to M. This is another antithetical proof, by which we mean indirect. So we wish to prove that M, the tangent, is perpendicular to AB, the radius. So we assume that it's not. Now this one's a little bit harder. It's a little bit harder to know what it is that one does next. But there's something we know, okay? Here's what we know. I'll tell you what, I'll draw a little picture here so we can actually see it on the video. So let's say that we have a line. We'll call that line L. Let's say that we have a point. We'll call that P that does not lie on L. We know that there does exist a segment from P to a point on L, call it Q perhaps, such that the segment is perpendicular to the line. We know this, okay? This is something that we talked about back in the chapter on, I think, inequality, and no doubt you find this quite plausible. But given a point and a line, there does exist from that point to that line a perpendicular, okay? Now, what we really said is this, okay? What we've said in the indirect proof is that M is not perpendicular to AB. That is, A to B is not the segment from A to M that is perpendicular to M. But a perpendicular does exist. So that means that it goes to another point, okay? Tell you what, there's another slide for this, but I'll just go ahead and draw it in. So if the path from A to B is not the perpendicular to M, then the perpendicular would have to go to some other point. Let us call it C, okay? So again, the logic here is this. A perpendicular path from A to the line does exist. And if it's not AB, then it goes to some other point on M that isn't B. Call that C, okay? So what we have really assumed then is this, is that there exists a point C, not identical to B, on M, such that AC is perpendicular to M. Okay? Now, do you see the problem with this? Hey, do you see it?
CA is longer than BA, but BA is the hypotenuse.
That's it. Okay. First of all, compare CA to BA. CA is a radius plus more. And how do we know that it has to be more? Because we said that M was a tangent. It intersects the circle precisely once, right? So AC goes along a radius, and then it continues on until it reaches the line. So AC is greater than a radius. That is, AC is greater than AB, which is a radius. However, if we have the right angle there at C, that means that AB is the hypotenuse of a right triangle, which means that it's the longest side, which means that AB is greater than AC. So we must say both that AC is greater than AB and that AB is greater than AC. But that's a contradiction. That cannot be true. So what then is the root of this? The root of this is our initial assumption when we said that AB is not perpendicular to M. So here then is the conclusion. If you have a line that's tangent to a circle and you construct in the radius to that point of tangency, the radius will be perpendicular to the tangent. So the two results then are these. The first result is that any line perpendicular to a radius at its endpoint on the circle is tangent to the circle, and conversely, if you have a tangent to a circle, the radius drawn to the point of tangency will be perpendicular to the tangent. So there's a very close connection between tangents and right angles, okay? And this is another part of the story, like chapter 12 out of, hundreds, about why it is that right angles and right triangles are so incredibly important within geometry. The concept of a tangent is a really very important idea. And there's a close connection between the concept of a tangent and a right angle. As a matter of fact, it's not a mischaracterization of calculus to say that half of it is concerned with tangents, not to circles, but to other kinds of curves as well. And you will see also in your calculus class a systematic connection between tangents, one of the core ideas in calculus, and right angles. So here it is. Now, that's it. That